6:30 exactly. All right, so let me begin. But first, folks, like in the last class, I will periodically stop and ask if you have understood what I said. And I expect you to raise your hands. I'll wait for you. Because seriously, if you're not paying attention enough to even realize that I have asked you to raise your hands, then you're probably wasting your time attending the lecture. On my part, if I don't see enough response, I will wait and it will slow us down and I won't finish my lecture. So please be attentive. And if you have questions, please ask. If you didn't understand something, please ask. If you understood everything, when I ask you if you have, please raise your hands. All right? Just so I know I can continue. Now, here's where we are. We're going to continue where we left off, but a quick recap. We've seen how neural networks can perform classification or regression. And so the next step that we took was to begin considering neural networks as generative models, which can model the distribution of any data so that we could draw samples from it. So the problem that we looked at was something like this. Given a collection of data of a specific class, we wanted to learn the distribution of the class so that when we drew samples from the distribution, it looked like an authentic member of that class. So for instance, if I learned the distribution of human faces, if I use the network to draw a sample from this distribution, it should give me a face. How do we characterize this distribution? That is the real question. So for this, we need to understand what it means for something to be a generative model. In statistical estimation, a generative model is a function or a computation model that characterizes the probability distribution of a given data. We can generally represent it as P of X semicolon theta, which means that this is a probability distribution over the random variable X, where X might be, for instance, images of faces, and theta are the parameters of the distribution. So the entire thing is a parametric function, and you can modify the distribution by modifying theta. But in reality, a model of this kind actually encodes a generative story for how the data are produced. And once we learn such a model, we can use it to compute the probability of observing a given data. Can you please mute yourselves? And we can also use it to generate samples. So we saw a couple of different examples. Gaussians, for instance, the Gaussian distribution is a generative model for this data whose distribution has the classic bell shape. This is a one-step generative model where in order to draw a sample, you just drew from one distribution. But we also saw other types of generative models like the Gaussian mixture distribution, where a distribution is modeled as a mixture of Gaussians. But the generative story behind it was that there's a two-step drawing process. In the first step, we select a Gaussian. In the second step, we draw an observation from the Gaussian. There's also another kind of multi-step generating process that we didn't get to in the last class. That's the linear Gaussian model, where, for instance, you might draw a sample from a standard Gaussian, put it through some kind of a transform, and then add data from another Gaussian to it to generate the final sample. In all of these cases, these are generative models for distributions. And when we want to learn the distribution for a given data, and we want to use a parametric form which encodes a generative story, then our objective is to learn the parameters theta such that the distribution that we learn best represents the data. And for this, we saw that we could use the principle that the data that we saw is very typical of the process. So of all the possible values of theta, we are going to pick the one theta that assigns the maximum probability to the actual data that we did observe. So we're going to find the theta that maximizes log of P of x semicolon theta, where x is your training and set of training data. If your training data consists of many training instances, you're going to choose the theta that maximizes the sum over all training instances of the log of the probability assigned to individual training instances by the model. So we saw all of this in the last class, and we saw how this gives us your classic formulae for Gaussians and for category distributions in the last class. We also saw that in many situations, our data are incomplete. They are missing something. For example, if I were trying to estimate a Gaussian distribution from data vectors, but some components of the vectors were missing, then you have incomplete data, and this makes it a challenge to estimate this distribution. Or in the case of a Gaussian mixture model, or you only observe the final data, you don't really know which Gaussian was selected, and this causes a problem. So in these situations, the actual distribution is defined on something other than what the model actually, what the data you actually get are. So here the distribution, in the case of the Gaussian, is over the entire vector, but you're only seeing a part of the vector. Here, the actual generating process has two steps, but you're seeing only the outcome of the final step. So the observed data are incomplete, and the maximum likelihood estimation procedure can only maximize the likelihood of what you have observed. That is the principle, but then the data are incomplete, and so we end up with a problem. And so we saw in this case that we can obtain the probability for the data that we have observed by marginalizing out the bits that we have not. So here, for example, you could marginalize out the components. H would represent all of these missing components for each vector. And so you can marginalize out by summing out or integrating out H to get P of O. And then the maximum likelihood estimate is simply going to look at the log of P of O, which is basically the sum or the integral over all H, where H is the missing information, the components here or the chosen Gaussian here. So this is going to be the log of the sum over all H of the joint probability of H and O. And this puts us in a situation where the function we are trying to optimize has a summation or an integral inside the log, and that becomes intractable. And so in this case, we had to take advantage of, or we had to use a different strategy. We did not directly maximize the log likelihood. Instead, we defined an empirical lower bound or an elbow for the log probability. We saw that the actual log probability of the data is lower bounded by the convex sum of the log of the joint probability of H and O divided by Q of H. So this term to the right was what we call an empirical lower bound. And this would hold for any probability distribution Q of H. Regardless of what Q of H you chose, if this is a valid probability distribution, then this term to the right is going to be a lower bound on the log probability of O. And this bound is tightest when Q of H is exactly equal to P of H given O. And so once we write out this lower bound, we get a nice iterative estimator where we can try to maximize this lower bound rather than P of O itself. And how does that work? We get a two-step process. We know that the log probability of the observed data, which is a function of the actual parameters theta, is lower bounded by this L. This L, I'm calling this a lower, L stands for lower bound. It doesn't stand for loss. So this lower bound is also a function of theta, but the lower bound is actually this convex combination of log of P of H comma O with parameter theta, the ratio of P of H comma O and Q of H. So does all of this is from the last class. How many of you remember this? Raise your hands if you remember all of this. Any questions about any of that? Any questions? Can I assume that this bit was clear enough that I don't have to go over it? Because everything depends on this. If you can assume it, then I will assume that is the case. Okay, so here is the two-step process that we get. In the two-step process, the lower bound is the convex combination over h of log of p of h comma o given divided by q of h, right? So what I will do is in the first step, I'll try to make this lower bound as tight as possible. And the way I will make it tight is that I'm going to fix theta. And I told you that this is a lower bound regardless of what you choose q of h to be. I'm going to try to choose the q of h that makes this lower bound extremely tight. So I will fix theta to the current estimate of theta and find the q of h that maximizes this lower bound. And observe that because this is maximizing q of h after fixing theta, this is going to be a function, this q hat of h, which is the q of h that maximizes the lower bound, is going to be a function of the current estimate of theta. Is that making sense? Yes, no? Oh, wait, this has to make sense, right? Okay. All right, so I have 20 hands raised. Guys, I will wait for 50 for the next time I ask this. Now I have chosen my q of h, right? So once I choose my q of h, I'm going to maximize the lower bound again, but this time with respect to theta. And the denominator over here is no longer a function of theta, so I can ignore it. So I'm just going to maximize the sum over h of q hat of h times log of p of h comma o with parameter theta. So the two-step process, fix theta, optimize q of h, then use q of h, and optimize with respect to theta. So this is a two-step process. Visually, how does that work? So I can write, let me just summarize the whole thing. I can just say that I have defined my lower bound, which is a function of two terms. One is the current estimate of theta, the other is the future estimate of theta. In the first step, I'm maximizing q given the current estimate of theta. In the second step, I'm fixing q and maximizing it with respect to theta. And then this theta itself is going to be, the new estimate of theta itself is going to be used to maximize q. So how does that work? Now, let's say this red function is the log likelihood. It's a function of theta. As I modify theta, you're going to get some log likelihood. I want to find the theta where this is maximum. Now, the q function over here is also going to, if I choose this q, right? This lower bound has two terms. One is this theta that goes into q. The other that is the theta that goes into log of p of h comma o, right? So this whole thing is also a function of theta, as you can observe. And so the lower bound function as a function of theta is going to be some other curve, shown by this blue curve. When I maximize it with respect to q, I'm pushing the lower bound curve as high as possible at the current estimate of theta, because I'm fixing theta. So if I keep modifying q, the function, this blue curve will change. So I'm going to keep searching through the q's till I find a q which makes this curve as close as possible to the red curve at the current estimate of theta. And eventually, if I choose q equals to exactly the posterior probability of h given theta, it will exactly touch the log likelihood of o given the current estimate of theta at this point, right? O given theta at the current estimate of theta. But the lower bound function itself as a function of theta is going to be something like this. It's always a lower bound, right? Now, if my q is not exactly equal to, I don't know where I mentioned it, somewhere here, right? If my q is not exactly equal to the posterior probability of h given theta, then this lower bound function is going to be slightly below this guy. The closer q approximate the posterior probability of x, the closer it is going to get to touching my function right here. But then now this blue curve is my auxiliary function given by this guy here, once I have optimized it with respect to q. So now I can optimize the blue curve with respect to theta. And when I optimize it, I'm going to find this value where my auxiliary function is maximum. And because my auxiliary function is always a lower bound on the log likelihood, so the difference between theta and theta k is the current estimate of theta, Denise, right? So like I said, in step 1, I have the current estimate of theta. I'm maximizing Q with respect to that. Does that make sense? Right. And so as I keep improving Q, even this auxiliary function, which is the lower bound function, is a function of theta, right? As I keep improving Q, eventually it's going to just touch this curve, but at the current estimate of theta. Otherwise, it's going to be slightly below that. Did that make sense? Yes, no? Any questions about this? Right. And so then I can maximize this with respect to theta, and I'm going to get my new estimate over here. So this I know because I've maximized my Q, and I know that my Q is a lower bound on P, log P, right? And my Q is more or less touching log P right here. I can expect that the log likelihood of the data, that is the red curve, will be, at this point, is going to be higher than the red curve over here. That will be my expectation. So now at this new estimate, I'm going to optimize my Q again. And if I optimize my Q again, with the new curve, my auxiliary lower bound curve function is going to look something like this. And then on this new function, I can again maximize my lower bound function. And then I'm going to get a new estimate of theta, which maximizes the lower bound function. And so I can expect that the actual log likelihood here is greater than the actual log likelihood here. So at that point, I can use that value of theta and optimize my Q of H again. It gives me a new lower bound function, which I can maximize. And I can repeat this process. And eventually, I'm going to find the value of theta where the entire function is maximized. So did that make sense, guys? I'll wait. So this is the basic idea. And we know this is, so is this guaranteed to work? When is the condition under which it's guaranteed to work? Does anybody want to take a chance? It doesn't have anything to do with convex. If my Q function is such that the blue curve touches the red curve at the current point, then I know that I'm always going to be, if I maximize Q, I'm going to be maximizing P, right? On the other hand, if my Q is not exactly the posterior of H, then log O given theta is the O semicolon theta is the log likelihood of the observed data, using theta as the current parameter for the model. That answer your question, Dennis? Right. So if my blue curve wasn't exactly touching the red curve, then maximizing the blue curve may not quite increase the red curve. But if it exactly touches the red curve, it is guaranteed to increase the red curve. Then maximizing the blue curve will increase the red curve. Does that make sense? So, any questions? No. Okay. And so when the blue curve exactly touches the red curve, you get Q of H is the posterior probability of H given X. And that is going to give you the expectation maximization algorithm. On the other hand, if it doesn't quite give you exactly the posterior probability, but it's only a close approximation to it, then the blue curve is going to be slightly below the red curve at this point. And then it's kind of an expectation, a belief that maximizing the blue curve will also increase the red value. Get you to a place, theta, which also increases the red function. So that was the theory. But the practical interpretation of this was that when you had incomplete of this data of this kind, you are sort of filling up these missing components, and you are re-estimating the model from the completed data. And specifically what you were doing was that you're filling up these missing components according to the optimized Q of H. And the optimal Q of H, of course, is when the Q of H is actually the posterior probability of the missing data given O. But if it's close enough, it will still work. And then once you have filled up the missing components, you re-estimated the data from the completed data. And there are two ways to do it. Once you have a Q of H, you can explicitly consider every possible value for the missing components with a posterior based proportionality, or you can simply sample Q of H to fill in the missing components. And of these, explicitly considering every possible value is the theoretically better thing to do, but it's only going to be feasible if that gives you a closed form mathematical formula, which it often won't. In those cases, you will have to use sampling. So any questions on things we've covered so far? This is just a recap from the last class. Any questions? If no questions, I will continue, right? So I'm going to switch topics. We began talking about principal component analysis, which looked unrelated, but is it? PCA is the problem of finding the principal subspace such that when all the data are approximated as lying on that subspace, then the approximation error, which is the squared lengths of all of these black lines, which is the error that you make when you project these black dots down onto the line here. You find the blue line so that this approximation error is minimized. So, for example, if this were all of your data, what you would be doing is searching through all possible lines until you found the line where such that the total squared length of all of these black lines is minimized. Basically, you're searching through all the subspaces to find the one with the minimum projection error. This was principal component analysis. And this can be done in closed form. If I assume that my principal subspace is represented by a bunch of unit length orthogonal vectors, which you can, then the projection of any data point onto the principal subspace is simply the inner product between the data point and the vector W, the basic vectors W, that represents the space. That is when the length of W is 1. In this case, the projection error is going to be the length of this perpendicular drop, which according to Pythagoras' theorem is the difference between the squared length of X and the squared length of the projection. And if you sum this, which is given by this term here, if you sum this over all of the training data and you minimize this with respect to the basis W, that gives you the standard eigenvalue decomposition formula that we are familiar with when we perform PCA. But then there's also an iterative solution. And the reason there's an iterative solution is this. In the general case, if I'm not assuming any restriction on the length of W, then there are two things we are trying to estimate. We are trying to estimate the base for the principal subspace. And for every data point, you're trying to find how this data point can be expressed in terms of these bases so that such that the data point is projected onto the principal subspace. In other words, you're trying to estimate the W, which represents the principal subspace. And then for each data point X, you're trying to find the weight Z such that Z times W is the closest approximation of X on the principal subspace. So once you realize this, that you're trying to actually approximate X, every X by some Z times W, then there's a two-step process. I can initialize my W, then fix the W and find the Z for every X. Then I can fix the Z for all the X's and find my W. So visually, here's what it would look like if those black data points are my data instances. I can initialize a subspace, the W, which is shown by the dark red arrow. Now, I'm going to project every data point onto this initial subspace. Think of this projection shown by the red dots as red balls that are attached to these black balls by some cable with tension whose tension is proportional to the squared length. These balls are allowed, you can either attach the ball to the surface or allow them to slide along the surface. Those are the only two movements possible, right? So I can initialize my subspace, and then I attach these balls to every one of these data points. If my subspace is fixed and I release the balls, what will they do? What will they do? Anybody? Imagine you've got a spring from this data point to this red ball, and the red ball is only allowed to slide along this line. And I release the ball. Where will it end up? Anyone? It's going to slide to the closest point distance to the black ones, right? So each of them is going to directly end up at a point which has the least tension on the red line. Now, I'm going to attach the balls after they got to that point so that they can no longer move on the line. But then I'm going to release the line and let it rotate around this hinge, and so that it can rotate and it can lengthen in proportion. Then what will happen? If I let this line rotate, what's going to happen? Anyone? What would happen?
Hello.
Guys, can you mute yourself? Yeah. Hello. Can you mute yourself? Drop out of class. Right? Hello. Can you mute yourself? Okay, so it's going to rotate till the total tension and all of the lines is minimized, right? Does make sense? At this point, it's allowed to rotate and stretch. Did this make sense? The hinge is the origin, yes. Right? Okay, now, assuming this made sense to you. Now I release the balls again, the red balls. What will happen to the red balls? Anyone? What will happen to the red balls if I release the red balls and let them slide along the line? They're going to slide to the new red point, to the closest point on the black line. Now I attach the red balls and let the line move again. What will happen? What will happen? It's going to rotate and give you a new line such that the total tension is minimized, right? Then I release the balls. They're going to fall again. At each step, the total tension in the lines is minimized. Do you see that? At each step, the total tension in the line is minimized, right? If you see that, raise your hands. So where will it stop? Where will it stop? Anyone? When the tension cannot be minimized any further, right? It's going to stop at a minimum. And so, or at least a local minimum. And so basically, this is an iterative way of performing PCA, correct? And so there are two different ways of doing PCA, not just your closed form solution. So what were you doing? If I look at it from the lens of things that we are familiar with, here's what we did. Initially, you fix the subspace by fixing W, and you estimated the Z's, the point on the surface, which is like letting the ball slide along the line. Then you fix the Z's, and then you rotated the space. You found the W such that the total tension was minimized, which is to say you minimize the error between the ZW and X. And so this is what the actual process looks like, right? In the first step, you found the Z. Then the next step from the Z, you found the X hat. You found the W, right? And you kept iterating this process. The whole thing just looks like an autoencoder. And so you could, when you actually, you did our autoencoder back when we were talking about it 2 weeks ago, 2 classes ago, what back propagation was doing was simultaneously optimizing both W and Z. But you can see how the whole thing can be viewed as just an autoencoder, where in the first step, since the Z that W you find here is the same as the W you have over here, you fix the W and found the Z. And the next step, you fix the Z and found the W, right? So there's one minor issue over here. There's scaling invariance. If I increase the length of W, I can decrease the magnitude of Z, right? And I'm still going to get the same overall Z times W solution. So the solution is not unique. And ideally, we would like a unique solution. So, if I scale up W by a factor of 2, I can scale down Z by a factor of 2, and everybody's happy. But then this means that there's a scaling factor, so invariance. To eliminate invariance, you can do one of two things. You can say that my W's must always be unit length. Then yes, and that will give you standard PCA. But there's a different way of doing it. I can also say that the Z's must have a variance of 1. And that too will give me the same subspace, because eventually the solution is the same, but the W's that you will get in the two cases are not going to be the same, because we're using different constraints. The subspace will be the same. The actual W's might be different, but you're still going to perform PCA. Did that make sense? Okay. All right. So beautiful, right? And so we can, this is our linear autoencoder basically. It can be constrained to give you a unique solution by simply saying the Z must have a variance of 1. How? We'll get to it. But then let's go back and look at what we are doing in the iterative solution. For every data vector, there is the term Z, which tells you where it must be projected on the surface, right? If you had the Z for every data vector, then you could determine the surface uniquely. On the other hand, if you had the surface, you could find the Z for every data vector. So what are we doing? We are initializing the basis for the plane, basically the subspace. Based on the subspace, we are computing the Z for every data instance. Then using this data, the Z's, we are updating the surface. And then using the updated surface, we are estimating the Z's. And we keep iterating this process till the whole thing converges. Does this look familiar? What does it look like? Anyone? Not just MLE. It looked specifically like the expectation maximization algorithm that we just saw, right? Where you're trying to maximize an empirical lower bound. And so it is in fact EM. But EM, we said, applies to generative models. So what is the generative model that we have over here? What is the generative model this distribution is encoding? This is basically like saying I have an autoencoder, except that on Z, I have a unit variance constraint. So this is like saying that my Z is coming from a standard Gaussian, has a standard Gaussian prior. It's being drawn from a standard Gaussian. And I'm trying to estimate the decoder such that this whole thing works while ensuring that Z has a Gaussian distribution. And now the decoder portion of this autoencoder actually is a generative model. Here's what you've got. Turns out that linear autoencoders with a unit variance constraint on Z have a generative story. It says that all the data have, the data are being generated by a two-step process. We first take a Gaussian step on the principal subspace. Then we take a Gaussian step exactly orthogonal to the principal subspace to generate the data point. And PCA, or linear autoencoders, find the plane, which is to say the basis for the plane, and the variance of this orthogonal noise. So the decoder portion of your linear encoder, which performs PCA, is a generative model. You're saying that Z is drawn from a k-dimensional isotropic Gaussian, where k is the dimensionality of the subspace. Then it's being put through a linear transform, where A is the basis matrix for the subspace. And then finally, at the output, you're adding a Gaussian noise with the constraint that the Gaussian noise must always be orthogonal to the plane. And so the covariance of this noise is low rank because it doesn't have any components on this plane. It only has components orthogonal to the plane. And what PCA is actually performing is obtaining a maximum likelihood estimate of A, which represents the basis of the subspace, and of D, which is the covariance of this noise. Did that make sense to you guys? A Gaussian step is basically you're adding, it's a Gaussian noise. You're drawing from a Gaussian and you're adding that to this guy, to this point. Did that answer you, Tian? So, okay, did this make sense? Yes, no? Okay. All right, and so the generative story, here's an alternative story. I can say that I have some initial space. This matrix A basically rotates and stretches this k-dimensional space and puts it into my higher dimensional data space. It's now a linear manifold in the data space. And so this isotropic circular or spherical distribution in the original space now becomes an ellipsoidal distribution in this data space. To draw any data point, I'm first going to draw some samples on the space from this ellipsoidal distribution and then add, which is Gaussian, and then I'm going to add Gaussian noise, which is orthogonal to this. So what is the overall distribution going to be? Anyone? It's going to be Gaussian, right? Because I'm drawing from a Gaussian, I'm putting it through a linear transform, and then I'm adding a Gaussian noise to it. So the probability density of X is going to be a Gaussian lying mostly close to a hyperplane. And all the correlated structure is going to be on the plane, and uncorrelated components are going to be orthogonal to the plane, right? So let me just pull up your first poem. All right, that was quick. Almost everybody responded. So everybody did. Let me end the poll. I think everybody got it right almost. So here's what it is, right? PCA actually performs maximum likelihood estimation of a generative model for the data. And the generative model is that in order to generate any point, the process first takes a Gaussian step on the principal hyperplane, followed by a Gaussian step perpendicular to the plane. It can also be estimated using EM. It's maximum likelihood estimation, which means you can use EM for it, and it assumes that the distribution of the data is Gaussian. That's centered on the principal hyperplane, right? And so what is the EM perspective over here? There's missing information for each data point, and the specific information that's missing is Z. If we knew Z, we could and X for every data point, then we could estimate A and B. But then we don't have it, and so if I had Z for every data instance, then the combination of A and Z and X is going to be the complete data. And then I can actually write out the log likelihood for the complete data, and then I can just optimize it to estimate A and D. And I'm not going to work through the math. This is just for a reference. Our problem is that we don't have Z. Z is missing. And so we went through this process where we initialized the parameters of the model, then we completed the data, and then used the completed data to re-estimate the model and iterate it. But then PCA has a drawback. It assumes that the noise is always orthogonal to the principal subspace. This is not always true, right? Where do we maximize the vector W? So when you're performing, look at this guy. Over here, my vector W became this matrix A Denix, that's all. The W is the basis of the principal subspace. I'm just calling it, I'm using my linear autoencoder representation and calling it A. Did that answer your question, Dennis? Yeah, that's correct, right? And A is basically the basis of our principal subspace, right? So where I have here, do I have a capital Z somewhere? Oh, Z is basically the collection of all the Z's for the training data. I just put them all into, it's just X is the complete set of training instances X, and Z is the complete set of Z's for all the training instances, that's all. I'm not getting into the details over here. The point was, if you look through it, you'd get the answer. It's written right here, right up here. So our issue is that our theta is just A and D, right? Those are the parameters of the model. Z goes with the training data. What are the parameters of this model? The parameters of the model are this A and the covariance of the noise D. Z is, every Z produces the corresponding X. So those, they are not parameters of the model. Did that answer your question, Denise? Yeah, correct. And then you're using the updated, we are completing the data set by filling in Z's, estimating A, then estimating A and D, then using the A and D to complete the data set again and repeating the process. Did that make sense? Right. And so now we have a problem here. PCA assumes that the noise is always orthogonal to the data, which is not true. Think about just closing your eyes and listening to the sound of the room. If there's nobody in the room, you're still going to hear voices in the room. Look at just random noise in an image. You can begin to see patterns in the noise. So noise in images, random noise, they can sound like look like actual images or sound like speech. So it's kind of not okay to assume that the noise is always orthogonal to your principal subspace. It can actually sometimes be aligned with the principal subspace. So how can I update this model to actually capture reality? Anyone? How can I update it? Any thoughts? What could I do? We're assuming here that the noise is always, just this model. We're assuming here that the noise is always orthogonal to the principal subspace. What can I do to generalize that? I can just say that my noise is full rank, correct? This is a simple step up. This would say that I can take a step along the principal subspace, but the noise can be in any direction from here. Does that make sense? Right? Easy, right? That's the simple first step, okay? So we're going to add full rank Gaussian uncorrelated noise that is independent of the position on the hyperplane. And so this gives us what is called a linear Gaussian model, which is that you have some low dimensional random variable, isotropic Gaussian, which is put through a linear transform. And to that, you add some full rank noise. And then because everything is Gaussian, the distribution of the linearly transformed Z, which is going to be A times X hat equals AZ, that's going to be a Gaussian. Assuming Z is zero mean, then X hat is zero mean, and the variance is simply going to be AA transpose. When I add full rank noise to it, this is still going to be Gaussian, but with zero mean, and the variance is AA transpose plus D, where D is the variance of the noise. And so if I get, so for every, now again, the parameters of the model are D and A. Yes, no, it will not. Z is going to be orthogonal to the subspace, always. Z is going to capture, assume that all the information in the data lies on the principal subspace. There is no noise, right? So, whereas noise can lie on the subspace, correct? And depending, if I allow D to be large, then I can end up with a completely different A, Denny's. If you're maximizing the likelihood of the data, then you're trying to minimize D, right? You're going to make the covariance as small as possible, right? It's like tension, right? The tension is like the log likelihood of the data. Denise, did that answer your question?
Yeah, I'm a little bit lost with the D part, Professor, here. Like, I understand why we have to add noise, I just do not understand why noise is something that we learn, because doesn't that give us just the like instinct to just minimize noise, because noise just increases the variability in the model?
Exactly, it does. So suppose, let me give you a picture over here, right? Suppose I have something of this kind. In which direction would you want your principal subspace to be for the noise to be minimum?
Oh, I see. I guess it would be like x1 is equal to x2.
Correct, right? So this is just like PCA, except that you're generalizing it and you're saying this is better than PCA. You're saying I'm not constraining the noise to be orthogonal to the subspace.
Okay, so just to clarify, the noise is effectively is it the like shifting around the line, shifting around the fixed line? Can I represent loss in that way? Sorry,
So,
can I represent the noise in that way?
so think about it this way. I'm just going to say that I'm saying that my data lies very close to a principal subspace. And it's most of the data is on the principal. So you can think of it as saying my data, the actual structure in my data lies on a linear manifold. And any variation off of it is noise.
Okay.
Right? I don't know if that answered your question. So basically you're saying to generate a data point, I'm taking a random Gaussian step on this plane. Then I'm drawing a little bit of random Gaussian noise and adding to it. That's the generative.
Yeah, we're basically reconstructing the data set by generating these points, right?
So that we are saying that the data set was generated according to a process that follows these rules.
Okay, that makes so much sense. Okay. Okay,
Right?
thank you.
Then you're saying, find me the parameters of the process.
I see. Okay, thank you.
Right? And so D would be jointly learned, right? And you can work through the arithmetic over here. I'm not going to spend a lot of time on the arithmetic, but again, you still have the same problem. You're only given the data X. For each data point, if I was given the corresponding Z, then I can actually write out the log likelihood, and I can optimize the log likelihood with respect to A and D, and I can find them both. But you don't actually have the Z for any data instance, right? So that this would give me a solution. But we don't actually have the data instance Z, it's incomplete. The observations are incomplete. And so you're going to complete the data in every possible way according to the P of Z given X, for which in this case, where everything is linear, we have a Gaussian formula, and we have a formula for the posterior probability. And so we can use that in my formulae and work through the arithmetic again. I'm not going to spend any time on the formulae. These are not relevant. The key point over here is the generative model itself, right? The generative model of this kind here had this assumption that all of your data basically the primary information in the data lies close to a linear manifold, and any variations off of that manifold are due to noise. And so what the model is doing is finding this principal manifold and the variance of the noise. So that is this generative model, where Z goes through a linear transform, and then you add some full dimensional noise to it to generate X. This is called factor analysis, and it's very similar to PCA, and it's been around forever. But did this model make sense? Right? And you can see how it models Gaussian distributions, right? So now here's the next step. First, here's a poll 2. Okay, 15 seconds, guys. All right. Okay. Most of you got there anyways. So let's see the results, right? Factor analysis, what are called linear Gaussian models, model the distribution of the data as Gaussian centered on a principal plane. This is just like PCA. The generative model is that in order to generate any point, the process first takes a Gaussian step on the principal plane, followed by the addition of isotropic Gaussian noise or full dimensional Gaussian noise, uncorrelated Gaussian noise. The parameters of the distribution are the bases of the hyperplane and the covariance of the noise. These can be easily estimated if the location of the first step on the principal hyperplane is known, because then you know exactly how much noise went into every data point. So from that, you can estimate the parameters of the noise. And knowing exactly where every data point lies on the plane means you also know the hyperplane. But because you don't know this first step, the actual estimation is performed using EM, which iteratively completes the data and then estimates the parameters, right? So I think there's now, I'm not sure which one is repeated. They're all the same. They're all different, right? Okay. So, but so you understand linear Gaussian models. They're modeling Gaussian distributions on a linear surface. But what if the data are not Gaussian, distributed close to a plane? What if the data have a distribution of this kind or a distribution of this kind? How would you do this, right? So in these cases, I can model this data as being some distribution that originally lay on a plane, then the plane has been warped, right? So we're going to do this. This is just like your linear Gaussian model, except that this linear transform is now going to be converted to a nonlinear transform. And so you're going to say that I have a nonlinear Gaussian model where f is a nonlinear function that produces a curved manifold. Remember how the decoder in your autoencoder sort of bent the surface into a higher dimension? So z is some lower dimensional plane. F of z is going to take it into the higher data dimension, and it's going to bend it into some sheet. And then on the output, after z has been transformed through f of z, you add some uncorrelated noise. So x, the actual data x you see is f of z plus some e. So if I think about it, if I want to model my data according to this, then I want to sort of initially come up with a function. In linear Gaussian models, we said the function was a plane. But here I'm going to find a function that warps. So in LGMs, the function was a linear transform that took the input plane and made it a plane in high dimensions. Now we are going to choose some function f of z that's going to take the input hyperplane and make it a bent surface in the higher dimensions. And then, so we're going to find this function. And now when I have a Gaussian distribution on the input plane, this is going to become a Gaussian distribution, but now on this curved surface. And then if I want to actually model the overall distribution of the data, I'm going to add some uncorrelated noise to the data points on this curved surface to get the overall distribution of the data. So is this making sense to you guys? Yes or no? It's a very simple idea, right? We just took something that we are always familiar with, PCA. We took it one step ahead and we said the noise was uncorrelated, but not necessarily orthogonal. And then we took the linear transform and we made it nonlinear. That's all we did. But this gives us our nonlinear Gaussian model. We have a nonlinear function that's going to take an input planar manifold and warp it into a curved manifold in the data space. So if I have a variable z that has an isotropic distribution in the input space, now this is going to result in some distribution on this curved manifold, where this distribution is going to follow the contours, the warped contours of the equal probability contours in the original space. So high density regions over here are going to get mapped into high density regions in this space after they have been transformed. And then the final observations are obtained by adding uncorrelated full dimensional Gaussian noise, right? So the generative process over here is to say, I'm drawing a Z from a standard distribution and transforming Z through f of Z, which is going to place the data point on some location on this manifold. And I'm going to draw some uncorrelated noise and add it to this point to get the final observation. So this is my actual generating process. It's a simple step from the linear Gaussian model. But then because f of Z can now model all kinds of complicated curves, it can model very complicated distributions. Any distribution that may be viewed as lying close to a curved k-dimensional surface in the data space can be modeled by this, captured by this model. So is this making sense? Questions? Okay. I'm assuming that it made sense to all of you, right? And so how to make sure wait. No, this is like adding non-linearities to your network, right, Ashwin? Adding many layers without non-linearities is simply going to give you a linear function, right? Autoencoder. Why is the noise not modeled with another f? You want to, so this is the model. The model is saying if I keep adding more and more, then there's no structure I'm learning. This noise could end up learning the structure of the data. We are literally trying to capture the surface on which the data lies. So the noise has to be an uncorrelated noise uncorrelated and close to it. This is an assumption. I'm not sure. To Ritu, that's just an assumption, right? Okay. If it works, it works. And let's see if it works. So the NLGM can actually model very complicated distributions. Any distribution that has the property as lying close to a curved k-dimensional surface in the data space. And in fact, the linear plane is just a special case. The key requirement is knowing the dimensionality of this surface, but that's our hyperparameter that we have to choose on our own, right? So when I'm designing the NLGM, what am I going to do? I'm going to guess the dimensionality of this manifold. I'm going to choose the function f. This is to answer the other question that we came up. This is the manifold warper. And then for this, we are going to use a neural network. And then we're just going to use our standard EM algorithm to learn everything, right? So does this make sense, guys? Right. So after this, it's just sort of tedium, okay? 23 minutes of tedium. I'm going to try to get through this quickly. I'm going to be given a collection of data X. From this X, I must learn the D, but now I must also learn the theta. Earlier, I just learned a linear transform. Now I must learn a nonlinear transform, and I'm going to use a maximum likelihood estimator. So we're going to go back for the same thing, right? If I gave you for every data instance X, if I told you which Z was drawn and put through the transformation, then if I gave you the function f of Z, then the way this data point was generated, because I already know Z and the function is deterministic, I already know X hat, right? And so now the distribution of X is simply going to be a Gaussian with variance D and the mean given by f of Z. Does that make sense? If I gave you Z for every X, then the probability of X given Z is simply going to be this guy, right? And does that make sense? Okay. And to actually get P of X, I have to multiply this by P of Z and integrate out, which makes the whole thing intractable. But then when we have an intractable problem of this kind, how did we solve it? You remember? We just went through it. I'm telling you, if I had Z for every X, Okay. First, let's go through pole 3. Fifteen seconds, guys. All right, let me stop this. Most of you did get it, right? So NLGMs are generative models. They model the distribution of the data as a Gaussian distributed on a curved manifold. The generative model is that in order to generate any point, the process first takes a Gaussian step along this manifold, followed by addition of Gaussian noise. The parameters of the distribution are parameters of the function that transform the k-dimensional plane in the input space to the k-dimensional manifold and the covariance of the noise. But then the NLGM, this I've not explained, is the decoder component of a variational autoencoder. So let's see how we can estimate the NLGM. If I had the Z for every data instance X, then the complete data are going to be a combination of X and Z. If I have the two, meaning I have X and I have the Z for every data instance, let's see how we can estimate the parameters of this model, right? This is going to be easy. Z is Gaussian, but it doesn't matter. Z is being given to you. So if I give you Z, then for every data instance X, I'm effectively giving you X hat, which equals F of Z, right? And so the actual X is going to be F of Z plus E, where Z is known. And so if I want to take the log likelihood of the complete data, X comma Z, I'm going to be summing over all of the training instances. And what I'd be summing is the log of the joint probability of P of X and Z, but then Z is given. So I can say I'm maximizing the summing of over all the training instances. I'm maximizing the log of P of X given Z, but P of X given Z is simply a Gaussian. So I'm maximizing the log of a Gaussian, which is simply given by the law, the Gaussian, of course, is X minus mean times covariance inverse times X minus mean, where the mean is simply, again, because Z is given, F of Z, right? And so now I can write out this loss function, which sums over, or this objective function, the likelihood function, which sums over all training instances, where for each training instance, I'm assuming Z is given. And this is simply the log likelihood of the Gaussian with F of Z as the mean for each X. So the mean is specific to every X. And this is just a quadratic, but it has this F of Z inside. In any case, it's an objective function, which is a nice functional form, a functional function of theta, which can be differentiated. And I can use gradient descent to optimize this function. So did this bit make sense? That if I had the Z for every X, I can actually write out a nice, clean likelihood function which can be maximized. That makes sense, right? I'll wait. If this made sense, just raise your hands. Okay. So here's what we have. Or I can take away the negative sign, and then it becomes a loss function, right? Which is I'm summing over all training instances, the negative, so of the log likelihood of each training instance, where the likelihood is computed using a Gaussian distribution with F of Z as the mean. And because we know Z, we know F of Z, right? This is easily solved. Unfortunately, we don't observe Z. So when we don't observe Z, what was the approach we took earlier? There's a D inverse over here, Advait. So D is the covariance of the noise. It's not the dimensionality. K was the dimensionality, right? That is the notation I used. So when we don't observe Z, what did we do earlier? What exactly did we do in EM? We guessed Z, right? What did we guess Z from? Sampled from what? We didn't sample from the observed data. We sampled Z from a function that closely approximated the posterior probability of Z given X, correct? Yes. You want to right? You want to sample Z from, we're going to complete the data. We don't know Z, the data are incomplete, we're going to complete the data. So there are two ways of doing it. We can complete Z by sampling in every possible way proportional to P of Z given X. Remember? And then we can compute the solution from the completed data, right? Or we could sample. We can draw samples from P of Z given X and compute the solution from the completed data. Everybody remember this? Raise your hands if you do, right? Okay. It's very simple, right? And using every possible value is to be preferred over sampling if the former produces tractable closed form solutions. Otherwise, we will use option 2. So let's work through the math. There's a lot of math over here, but I'm going to try to fly through it in 15 minutes. The posterior probability P of Z given X is P of X given Z times P of Z divided by P of X. This denominator, P of X, is actually a distribution along the closed manifold, and it's not tractable, so we're not going to be actually able to get P of Z given X. Instead, we are going to try to come up with a Q of Z, which approximates P of Z as closely as possible. And if you go back and remember those functions, the plots that I drew, when Q of Z is exactly equal to P of Z given X, our lower bound function touched the log likelihood function. So it gave us some guarantees. But if it approximates it, it won't quite touch it. So maximizing the lower bound function is not necessarily guaranteed to increase the log likelihood in every step, but it's the best we can do, right? So to make this work as well as possible, we want Q of Z to be as close to P of Z given X as possible. Specifically, we're going to assume that Q of Z for any given X is a Gaussian with a mean and a variance, which are both functions of X, and this estimator itself has a parameter phi. Is this making sense to you guys? Right? And now I'm going to use Q of Z given X, Z, as my proxy of P of Z given X. And I'm going to use that for optimization. And so here's what I will do. I'm going to initialize, this is a neural network, and these two are also obtained from a neural network. I'm just going to initialize my theta. And I'm going to initialize my parameters of this network. I'm going to initialize my theta. And then for any given theta, I'm going to try to estimate the parameters of these model to give you the best Q of Z. Then I'm going to complete, this should have been Z comma X. Then I'm going to complete the data using Z comma X and then re-estimate F. That's the whole thing. So here is the overall process. For each training data instance S, I'm going to find the best mu and sigma to such that this Gaussian, or I'm going to find the mu and sigma such that this Gaussian most closely approximates the posterior probability of Z given X. Then I'm going to sample from that and use those samples along with this X to estimate theta. And I already know if I have Z and if I have X, I can estimate theta. So how does one sample from this Gaussian? This Gaussian has a mean mu X and a variance sigma X. And so we're going to use a standard reparameterization trick to sample the Gaussian. We all of us know how to write code to draw Z from a standard Gaussian. So what we will do is I will draw some epsilon from a standard Gaussian. Then I'm going to scale it by the square root of the covariance of the Gaussian, basically by the standard deviation of the Gaussian, and then add the mean to it. And this scaled and shifted version is now going to be a sample from the Gaussian with mean mu and variance sigma. So did this make sense to you guys? I flew through it, but did that make sense? Right? And now the reason this is important is that you're going to have to remember this. I can find out how varying the parameter phi that is used to compute mu and sigma will vary z. So I can compute the derivative of z with respect to mu, with respect to phi, which is simply going to be the derivative of mu with respect to phi. Mu is a function, and times this epsilon times the derivative of the square root of sigma with respect to phi. This is directly from this formula over here. So we know how to compute the derivative of z, the sample, with respect to the parameters of mu and sigma. So at this point, we know how to sample z, how to perform this step, right? So now that I know how to perform this step, let me see how I can use this z and this x for them to estimate theta. And that's easy. If I know the z for every data instance, then we've already seen that I can write out the log likelihood, or rather the negative log likelihood of the entire training data, because for every x, I also have the z. And this term can be optimized with respect to theta and d using standard gradient descent, right? And in particular, if I assume that my noise has is a diagonal covariance Gaussian where all the diagonal entries are identical, then this loss function becomes even simpler. And this can be differentiated with respect to both the variance of the noise and the network parameters. And you can estimate the network parameters. So is this making sense? Yes or no? Okay, this is very simple, right? So now, if I have sampled z and completed each data instance, I know how to compute theta. The one challenge remains: how do I actually optimize this function? Remember, this function has to approximate the posterior probability of z given x as closely as possible, which means I have to estimate these phi's such that this Gaussian with mu x and sigma x as the mean and variance approximates p of z given x for every data instance x as closely as possible. Now, we want this p of qzx to approximate p of z given x as closely as possible, right? So the way we'll do it is that I'll try to minimize the error between these two guys. Define a divergence between qzx and p of z given x, and minimize it with respect to phi. And if I follow the literature and throw a bunch of formulae at you, this is what you will see in any paper. It's very easy to follow, obviously, and that now the lecture can be completed. But how many of you would just get this if you saw this? Anyone? I don't know about you. It wouldn't make sense to me, right? So, and there are a bunch of people who kept their hands permanently raised, but I think most of you wouldn't, right? So let's try again, okay? Here's what we want to do. Assume that I have completed the data using Q of Z, right? Guys, I'm going to run a few minutes over, but bear with me, right? And then, so I can say that each data instance, each X is completed with many versions of Z, right? As we saw earlier. But for now, I'm going to assume that for each data instance, I got only one Z that I sampled to complete it, okay? So then if I represent the completed data instances as X comma Z, then the posterior probability of Z given X for all the data instances is going to be the product over all training instances of the P of Z given X for every single training instance. If I take the log likelihood of this, it's going to be the sum over all training instances of log of P of Z given X. the corresponding approximation is going to be the sum over all training instances of log of Q of Z comma X, right? And so the error is going to be the discrepancy between these two guys. And I'm going to estimate phi, which are the parameters of mu and sigma here, to minimize this discrepancy. So I'm going to be minimizing log of QZ comma X, which is the sum over all training instances. So I'm going to be minimizing these difference between the log of Q of Z comma X and log of P of Z given X, which is the sum over all training instances of the log of QZX for that training instance minus log of P of Z given X for that training instance. And by Bayes' rule, I can write P of Z given X as P of Z times P of X given Z divided by P of X. So plugging this in over here, this log of P of Z given X is going to be minus log P of Z minus P of log X given Z semicolon theta. This is going to depend on theta because, the relationship between Z and X is governed by theta, plus log of, because X is in the denominator, this will become a plus, right? So is this making sense to you guys? This formula over here. Questions, anybody? I'm just going to go through this. Okay. So now modifying the phi modifies the mean and the variance of Z. So it influences Z, right? Because it influences Z, P of Z is going to be a function of phi, right? Because this is over all the Z's in your training set, right? After completion. And the specific Z's that you saw depend on phi. Similarly, P of X given Z is also going to depend on phi because modifying phi changes Q, and so changes the mean and the variance, which means that it changes the samples that you would get. So this too is going to be a function of phi. This term, on the other hand, has no Z in it and does not depend on phi, so it can be ignored. So we're only going to be minimizing the sum over all training instances of log of Q minus log of P of Z minus log of P of X given Z, right? And so again, how do we complete the data for training? Let's go back through the whole complete training pipeline. Here's what we had. This is the entire this upper portion is your nonlinear Gaussian model. This lower portion is what you were using to complete the data for training, right? So this gives you Q of Z. This lower portion gives you Q of Z. So to estimate theta, you're sampling Q of Z, and using X and Z, you're estimating theta. To estimate phi, now for each of those Z's, you have to find out how much perturbing those Z's will make X more plausible, right? Because it's a maximum likelihood estimator and you want to make X more plausible. But then the perturbation of the Z depends on the perturbation of phi, right? And so you want to find out how much perturbing the Z will make X more plausible, while simultaneously also making Z more Gaussian. And so basically you're saying, how much will perturbing Z increase the log likelihood of X, while also making Z more Gaussian? And Z can be perturbed by perturbing phi. So the question sort of translates to how do I perturb phi such that the resulting Z's make X more likely and are more likely to be Gaussian. And so to estimate the X, so the sample Z that you get, there are two ways of completing the data. You can complete the data using every possible value of Z or drawing samples, as we saw mentioned earlier, right? So it turns out that this portion of the formula can be computed in closed form if you consider every possible value of Z that you can sample. This portion cannot. So it turns out that for this first portion, we'll assume every possible value of Z, which just gives you the KL divergence between QZX and P of Z, right? And P of Z we saw was a standard Gaussian. The standard, because P of Z is the standard Gaussian that goes into the nonlinear Gaussian model. And the second term is simply P of X given Z. And so once we look at that, the Kullback-Leibler divergence between any two Gaussian distributions has a nice closed form, which is given by this term here, which I won't get into. Look at the slides. And we saw earlier what this term was, which is that if I know the Z's, we just ended up with a log likelihood that was a function of theta, right? But also a function of Z. And so I can plug both these terms in and I get a function, a loss function that has two components to it. The first is the KL divergence between the posterior probability Gaussian and the standard Gaussian. And the second is the negative log likelihood of the X given the sample Z. And that I can compute the derivative of that by taking the derivative with respect to phi. Again, I'm not working with the math, showing you the math. The chain rule is going to require the derivative of Z given the parameters of the Gaussian, of the mean and the variance. And all of these can be plugged in to so this gives me the derivative of the loss that is used to optimize the Q with respect to the parameters of the mean and the variance. Again, I'm not working through the math. I'm just trying to convey the concept. I don't think anybody is going to remember the math, but if you go through the slides, it will all be very clear. So now here is the overall training pipeline. I'm going to initialize all of my network parameters. I'm going to sample the Z's from my Q. And using the Z's and the X, I can define a loss function, which I can optimize for theta. Then using the theta, now I can go back and I can, but then using the same Z's, I can go back and optimize, and the theta, I can optimize the loss function that I had for Q to estimate the phi. Instead of doing this in two separate steps, I can combine them into a single loss function because this component of the loss function is common. The term here and the term here are the same. And so I can just write one loss function end to end, which can be optimized for estimating both theta and phi, right? So this last portion was probably too quick, but I promise you that if I spend half an hour explaining it when you're gone from the class, you won't remember it. But you can sort of go through the slides and the whole thing will sort of make sense. And then once the whole thing is trained, the portion that estimated Q of Q can be discarded. And this is your generative model. It's a nonlinear Gaussian model. And now if you randomly sample from Z and pass it through the function F and add a little bit of noise, it should give you data similar to your training data. And where are the neural networks? This F is going to be a neural network, and this mu and sigma, they too are estimated using a neural network with parameter phi. And so this whole thing is called the variational autoencoder. The portion that estimates the parameters of the Q function is called the encoder. The portion that generates data from the Z is called a decoder. And Z is the latent space representation of the data. So given any data instance X, you can compute the posterior probability of Z. And that's the posterior distribution of the latent space representation of X. The mean of this Q, this mu, is the most likely value of Z. And this can be used to generate new data, right? I'll skip this part. And so this is a variational autoencoder. VAEs are unfortunately strictly generative models. They can be used to generate samples of data, but you cannot use them to compute the likelihood of data because P of X is not tractable. Nevertheless, we've seen them. They're very effective as generators. Here are some early results from VAEs, where in this case, Carl Dorsch, who introduced the whole concept, use them to learn the distribution of MNIST data. And then when you randomly sample Z's over here and pass them through F, they give you things that look like digits. Or this was a VAE trained on faces. Now, if you randomly sample Z from a standard Gaussian and pass it through F, the result is something that looks like faces. And they also showed that if you consider the whole model, then for any data instance, you can actually compute the mu and sigma, right? So if I take two faces, say this guy and this guy, each of them is going to come up with a mu and a sigma. We can assume a common sigma. Then if I slide the mu, the mean, from the value that it had for this one to the value that it had for this one, and pass each of those means through the decoder, the data generated by the decoder actually smoothly slides from this face to this face. So some very nice results. So I'm sorry for having rushed through the tail end, but I'm happy to answer questions on Piazza, or maybe do another 5 or 10 minutes later if you want. But VAEs are basically simple nonlinear extensions of linear Gaussian models. They're excellent generative models for the distribution of a data. And there are various extensions such as conditional VAEs, which model conditional distributions, fairly straightforward. They've also been embedded into dynamical system models where P of Z can be made something else than a Gaussian. And in all cases, the arithmetic is very simple. It's similar to what I presented here. When you read it, it might sound complex, but conceptually, the idea that you're generating Z for each X, and then you're using that X to learn the relationship, learn the decoder, that idea still holds. So I'll stop right here. I've gone 6 minutes over, and I'll stop the recording.